Okay, so in the last class we initiated the concept of buckling, which is an instability that may occur in the elastic region of loading, right? So there are multiple types. One is when the post-buckling path is stable. One is when post-buckling path is not stable. The other is snap-through, when there exists a post-buckling path, but it's far away from the current equilibrium position, right? And then we are trying to understand how buckling essentially plays a role when you have to understand systems. So we'll start with the simple systems. We have single degree of freedom system. Then we'll move on to probably 2 degree of freedom systems. And then we will move on to beams, which is infinite degree of freedom, right? A beam is a continuous body, so it can deform. It will become infinite degree of freedom system. So in this system, we have a rigid bar, and we are trying to solve it for critical load at which buckling occurs, and then what happens when buckling has occurred. So we made an assumption that the deformations are small, so theta is small, and this was the initial position when the rigid bar was vertically upwards. In another position, another equilibrium position, this bar is at an angle theta. Okay, so what we will do is write the total potential for this system, total potential energy. So there is a spring which is attached at a distance a from the hinge. So that potential energy of the spring is equal to half k a theta square, where a theta is the deflection in the spring. So half kx square is the potential energy of the spring. And now we have to write the potential due to applied external applied load P. So how do we define this? We define this as the potential at the starting point minus the potential at the final point, right? So let's say my starting point is present here, and my coordinate goes in this direction, and my coordinate is z. So P times z0 minus z will be the potential at the initial point minus the final point. So z0 is 0 because my coordinate starts from here, and z is equal to this distance. In this axis, it was initially at this point, and now it traversed to a lower point because of the application of load P. So if this distance is my L, the length of the bar, and now L is this distance, right? So simple trigonometry, this distance will become L cosine theta. So this will be L minus L cosine theta. Make sense? We have to find this distance z, so we can subtract L with the projection of this bar on this axis, and projection is L cosine theta. So 1 minus cosine theta times L becomes z. So we can write our total potential ut is us plus up and for calculation of up, we will substitute the value of z in this expression. So it becomes half k a theta square minus p times L 1 minus cosine theta. Any questions at this point? Okay, so what do we do now if we want to find a critical path or a critical load? We would identify an equilibrium position, right? So we will differentiate this expression with theta, that's our degree of freedom. So essentially what we are doing is we are applying the principle of stationary total potential energy, which states that there exists an equilibrium position if the potential change in the or the variation in the potential goes to 0 for any arbitrary generalized coordinate, which is theta in this case. So we will differentiate the total potential, and we get minus PL sine theta plus Ka square theta is equal to 0. So we have small theta assumption. That would give us sine theta, which is approximately equal to theta for small angles. So we can say that minus PL theta plus Ka square theta is equal to 0. So rearranging terms, we get minus PL plus Ka square times theta is equal to 0. So solutions to this equation are theta is equal to 0, which is a trivial solution. What happens when theta is 0? This bar, which was in vertical position, remains in vertical position, right? So that's the trivial solution. Then we have another solution where PL is equal to Ka square, which gives a value for P as Ka square over L, right? Okay. So at this point in this rigid bar, we have equilibrium condition. And if P becomes greater than Ka square over L, we have buckling. So our P is the critical load. Okay, so P is the critical load Ka square over L at which buckling occurs. And remember, we have small theta assumption. So now we will see what happens in the post buckling path. So in the post buckling path, we will now apply the principle of minimum total potential energy, which states that if the potential energy, or if the second derivative of the potential energy is greater than 0, then we have a minimum, right? We have a minimum potential. So let's differentiate this expression again with theta. So we'll get Ka square minus PL okay. So on differentiation, or the second order differential gives us Ka square minus PL, and I'd like to show how this really plays a role. So let's say this is my axis theta, and I have the vertical axis on which I'm plotting the P PL over Ka square. So our P critical is Ka square over L. It means that PL over Ka square is 1. So at this point, where the magnitude of PL over Ka square becomes 1, till this point, every position is an equilibrium position, right? All these points, they are essentially stable. There is no buckling in this case. And then when it goes beyond the load, when PL becomes greater than Ka square, then we have essentially two solutions. One is when theta is 0. This is the trivial solution. So the bar remains in equilibrium when theta is 0. Right? And then if PL is equal to Ka square, which will be this axis, on this axis we have equilibrium points, right? When PL is equal to Ka square, there is equilibrium, so this horizontal axis, and then when theta is 0, the bar does not buckle or move, so those are all equilibrium positions. And this, of course, is in the near vicinity of 0, because this is small theta assumption, right? So we cannot go very far from the 0 position. Okay, so in this case, if PL is equal to Ka square, then we have equilibrium. Now, the second order derivative we found out, Ka square minus PL, and it should be greater than 0 for potential to be minimum. So essentially, Ka square minus PL is greater than 0. So PL is less than Ka square. So P should be less than Ka square over L. Or in other words, in this variable, we can say PL over Ka square should be less than 1. So this is the condition for post-buckling path to be stable. Okay.
Yes, that's a quick question.
Yeah.
When you first applied this small angle condition, you had sine of square theta go to theta squared. And then when you applied the small angle assumption again, wouldn't that would now be cosine of theta squared? In the derivative, wouldn't that go to 0? Meaning, I don't see how you could apply the same small angle assumption twice, since you have a sine term and a cosine term, which would flip. One of the terms should go to 0.
Which of these expressions?
So the first time you apply the small angle assumption, you make the sine squared term go to this you make it go to theta squared.
So I make the sine theta go to theta.
Yes. And then you take the derivative of that. So how is that derivative still valid if you apply this small angle assumption again?
So
So the derivative, in my mind, the derivative will be different in that case.
So if you
apply the small angle assumption.
You can take the derivative of sine theta to be cosine theta.
Yes.
and then you can apply small angle assumption.
And then wouldn't it just go to 0?
I think
Or just 1?
cosine theta, if theta is small, it becomes 1. But generally, we take 1 minus theta square over 2, and then we see where we can neglect this. If it becomes theta cube, or if it has some multiplication with theta, then we can neglect this term. Otherwise, we mostly take it as 1 minus theta square over 2. And then if you have to differentiate this expression, you differentiate this expression with theta, it will give the same results. For example, differentiation of cosine theta is minus sine theta, right? If you differentiate here with respect to theta, you get minus theta.
Okay.
So when you apply small angle assumptions on cosine theta, it is mostly 1 minus theta square over 2.
Okay.
Yeah.
Thank you.
Essentially what I did here was there exists series expansions for sine theta, cosine theta, and I am taking the first two terms in that series. Okay, so this was the energy approach where we write the total potential in the system, and then we use our principles, the stationary potential energy and principle of minimum total potential energy, to solve for the conditions that we need. But there are other methods, as we discussed. We can either use the classical approach, in which we are writing the equilibrium equations, or the dynamics approach or the kinetic approach, in which we write the dynamic equation of motion. So I will give a very brief example of how to solve using those methods, but because those methods become very complex when we have, let's say, no assumptions involved, so we will stick to the potential energy approach for rest of the problems. Okay, so let's say we use the classical approach. So to use the classical approach, we will write the equation or the governing, we will essentially write the moment at the hinge, and for equilibrium we know that the moment will go to 0, because if there is a moment which is non-zero at the hinge, then there will be a motion, right? So let's write the expression for the moment at the hinge. Let's say this point is O. Okay, what are the forces in the system? One is the externally applied load, and the second is the spring force. So what will be the moment because of the externally applied load? Negative? Negative P theta? L theta? Okay. And then we have a spring force, which is anti-clockwise moment, K A theta times we want this distance. What will be this distance? This distance will be A, right? Because small angle assumptions. So this distance become A theta, and this is A. So it should be 0. If there is non-zero moment at the hinge, then there is no equilibrium. So for equilibrium, this should go to 0. So we say that we have minus PL plus KA square times theta is equal to 0, which is a similar equation to that what we obtained from energy methods, right? Here we have minus PL theta plus KA square theta is 0. So we obtained the similar equation here for equilibrium, and now we can carry the same solution. Theta is 0 is a trivial solution, and then we have minus PL plus Ka square is equal to 0 for the post-buckling. Then there is another approach which we call as dynamic approach. So in this we have the dynamic equation of motion. So there will be an inertia term I theta double dot plus m is equal to 0, and we calculated the moment in the previous case. So I theta double dot minus PL minus Ka square theta is equal to 0, right? So this is a second order differential equation, ordinary differential equation. For a bounded solution, we need this coefficient to be positive. If this coefficient is negative, we have a hyperbolic solution. If this coefficient is positive, we have a simple harmonic motion which has a bounded solution, right? So minus PL minus Ka square times theta is greater than 0 for stability or bounded trigonometric solution. Otherwise, we have a hyperbolic unbounded solution, which is unstable. If we have an hyperbolic unbounded solution, the magnitude will keep increasing, so we won't have stability. And for calculating the equilibrium position in a dynamics problem, we say that the frequency is 0 at the critical situation, which is the equilibrium position. So if we rewrite this equation, we have theta double dot minus PL minus Ka square theta over I as 0. So the frequency in this case is this coefficient, which is omega square, and omega square is the natural frequency. Right, and we know that omega is equal to 2 pi f. So from that you can get your equilibrium condition. So these methods are possible or feasible to calculate equilibrium positions and the post-buckling path, but they become very complex if we have, let's say, large trigonometric expressions or nonlinear equations. Especially if you consider large deformations, the dynamics approach becomes highly nonlinear. So we'll stick to the energy methods and would consider large deformations in that problem. So we have a bar, applied load P, undergoing the same deformation. In this case, theta is now large. Okay, so the spring force here is K times A tan theta. The reaction force here will be perpendicular to the bar, which is R. Any questions about the reaction force? So if you recall that the system we have is a bar with a ring which is attached to a spring. So this is a frictionless ring which is attached to the bar, and it can move up and down in the bar. So when this bar undergoes large deformations, the reaction force always remains perpendicular to this rigid bar. Okay, so that's why the reaction force which I've applied in the free body diagram is perpendicular to this bar, but the spring force acts in the horizontal direction. So that's why the spring force is Ka tan theta, which is applied in the horizontal direction. Okay, and then this expression, or this distance now, is L sine theta instead of L theta, because we don't have any small angle assumption anymore. So sine theta will show up in the equations. We already calculated this distance to be A tan theta, and this distance to be A over cosine theta. Okay. So let's write the energy expression. The total potential energy for this system will be, because of the spring and because of the externally applied load. So what's the potential energy of the spring is half Ka tan theta square. Ka tan theta times A tan theta. What will be the potential due to the externally applied load? Is there any difference? Did we make any assumption previously while calculating this distance? No, right? We did not make any assumption while calculating that distance, so it still remains L 1 minus cosine theta. So we have the total potential energy in the system. Now we would like to find our critical conditions for primary and secondary path. So we differentiate it. We apply the principle of stationary total potential energy. So we get K A square sine theta over cosine square theta minus PL sine theta. So rearranging the terms again, we get Ka square over over cosine square theta minus PL times sine theta is equal to 0. So we have two solutions again. We have sine theta is equal to 0, and we have ka square over cosine square theta minus PL equals to 0, right? So this will happen when theta is equal to 0. Of course, we are not considering the other solutions that it's pi, because our bar cannot go completely in opposite direction. So let's draw that profile again. We have theta in this axis, and we have PL over Ka square on this axis, right? So the primary path is theta 0, that if theta remains 0, then this bar remains vertical and there is no buckling, right? So we have a stable path when theta is 0. Then the other condition is PL, Ka square over cosine square theta minus PL is equal to 0, right? So this is our secondary path. And this, let's say if this is 1, then that's the graph for 1 over cosine square theta. Okay, so this is our secondary path. These are all the points which satisfy the second equation, Ka square over cosine square theta minus PL. So we don't know whether our secondary path is stable or not. If we have to find that out, we have to do the second order differential of potential energy with the degree of freedom theta, right? So the second order differential with respect to theta becomes Ka square minus cosine cube theta minus PL times cosine theta plus 3 Ka square sine square theta over cosine 4 theta. So for the primary path, when theta is 0, this expression simplifies down to Ka square minus PL, and this has to be greater than 0 and it's greater than 0 for P less than Ka square over L, and if it's less than 0, which is for P greater than Ka square over L, this would be unstable, right? So for post critical condition, So when theta is 0, that's our primary path, we identify what are the conditions for stability, right? So we get that if P is less than Ka square over L, then we will have a stable bifurcation. Now when P, so using this primary path we can find the P critical, which is P is equal to Ka square over L, right? So P critical is equal to Ka square over L. So this is the critical condition. So for post critical condition, we will use this solution in this expression and simplify that expression. So we get that the second order derivative for the post critical condition in the secondary path is this expression. So we have this cosine cube.
So we're not looking at that, like the primary and secondary from that case.
Oh yes. But then yeah, it should be cosine square theta, but we'll have to check the simplification then. But I think it should simplify down to this expression. So it becomes 3Ka square sine square theta over cosine raised to power 4 theta, and we can see that all the trigonometric terms are even powers, so this term will always be positive, so our potential energy is minimum, right? So it means that this post buckling path is stable. So all these points here are stable. So the post buckling path becomes stable. Why? Because post buckling path for the secondary solution is greater than 0. So the potential energy will always be a minimum. We will have stable bifurcation, a stable post buckling path. Any questions at this point? And of course, this is bounded to cosine inverse A over L, and this is minus cosine inverse A over L. Pi by 2 is somewhere here, and then so these bounds are just when we just assume that theta is between these conditions. It is still large angle assumption, but we are just giving a bound for theta, that it cannot deform beyond that location. Okay, so let's look at a couple of examples. Let's say we have a system where this distance is L. So we have two rigid bars of length L joined at a hinge. So hinge doesn't take any moment, they can rotate with respect to each other, and there is a spring attached at the hinge, which is a vertical spring with spring constant K. and they both are on rollers with a compressive load P applied at the ends of the rigid bar. So, how many degrees of freedom are present in this system? 2. What is the degree of freedom in this system? X and theta. So x in this direction and theta is the angle of deformation. Can they both be related with each other? So the degree of freedom in the system is 1 because they both can be related to each other. So in this system you can just define a degree of freedom which is delta, the distance of this hinge which is from the top point. So this system in a deformed state would look like and this horizontal distance will be L square minus delta square square root, because this distance is L, right? So you can define 1 degree of freedom in the system which is delta and write all the distances in this geometry with respect to delta. Now what you have to do is standard procedure, write the potential energy, differentiate it once to get the stability paths or critical conditions, and then you have to calculate the post buckling path by calculating the second order differential of potential energy and finding where it is positive, right? Let me give you an expression for the potential energy. It's half k delta square minus p times 2l minus 2l square minus delta square square root so that becomes the total potential energy. So for equilibrium, we differentiate with respect to delta and we get k delta plus 2p over square root of L square minus delta square times minus 2 delta. So some simplification, essentially we get k delta minus 2p delta over square root of L square minus delta square is equal to 0. So again we have two solutions. One is delta 0 and that's the trivial solution we have. or we call it primary path. And then we have k minus 2p over L is equal to 0, where p critical is kl over 2. So we found our primary path, which is, let's say I draw here, theta p 2p over kl. This is 1. So all these points on the primary path are in equilibrium. And then the critical point is when p becomes kl over 2. So now let's look at for stability. We will differentiate the total potential energy with respect to delta up to the second order. So we get k minus 2p over square root of L square minus delta square minus 2p delta square over L square minus delta square raised to power 3 over 2. So we will analyze this equation in the next class to find the post-buckling path, whether it is stable or not. Yeah.
Is theta or is theta delta? Is delta,
Oh,
are we
yeah,
graphing against? Okay.
Sorry, yeah. Got confused between the problems.
Yeah, that's fine. I just want to make sure.
So what we have to do now is find whether this second order differential is greater than 0 for the secondary path and the primary path. And if it is, then we will have a stable bifurcation or the stable post-buckling secondary path. But if it's not, then we will not have a stable path. So it will become unstable. Yeah.
Are we assuming small data?
We are assuming that delta is smaller than the L.
Oh, that's right.
Yeah. So that's why there were some simplifications here.
After 1.